Okay, so we're gonna begin. So as a very first topic of this course, we're gonna cover the basic information security principles. So these principles explain, well, first of all, the purpose of information security in the first place, and also we're gonna learn about the 8 principles that security engineers and security researchers abide by even to this day. So, all right, so who has heard of the CIA triad? Okay, about 3. So this actually has nothing to do with the Central Information Agency. So CIA is an acronym, stands for confidentiality, integrity, and availability. So these 3 goals of information security is said to be the 3 main goals of any information security systems. So C stands for confidentiality, and according to the English dictionary, confidentiality means the state of keeping or being kept secret or private. So this is a principle that controls access to information only to those who are authorized. So we're gonna get to the authorization part shortly. Okay, so what is one example of confidentiality? What do we do to preserve confidentiality of information? Yep.
Authorize like user lists, like access control lists.
Mm-hmm. So that's one example. For example, I can see everyone's grade on iCampus, but you have to be authorized to view those information. Good. So confidentiality and history. Confidentiality and information security has a very long history, but I guess the modern form of encryption or cipher systems were first introduced during the Second World War. So the Germans used cipher machine, so they invented a machine that automatically encrypts their messages so they can keep their chain of command secure. So this machine ensured the confidentiality of the German communication channel and until Alan Turing broke the code with his own machine. So confidentiality has a long history, especially it is often associated with wars and information security agencies and so forth. So yeah, confidentiality is basically keeping the information unreadable or unrecognizable from those who are not authorized. And encryption and decryption is probably the most common example of, or most common way to maintain confidentiality. All right, so integrity. According to the dictionary, this is about internal consistency or lack of corruption in electronic data. So this is obviously a new definition of integrity, right? So integrity is a security principle that guarantees a data or message has not been altered by unauthorized entities. And what is one example of integrity in computing systems? Yeah.
The bar in the website that's
in the lock icon.
Yeah.
So that's actually coming up later, but it's actually both about confidentiality and integrity. So confidentiality is, for instance, encryption, right? Making the data unrecognizable from your enemies. Integrity is about preventing corruption or recognizing that there was a corruption. So historically, people have tried to maintain integrity of their messages through one of these seals on the letter envelopes, right? At the time, common people did not have the technology to counterfeit this type of complex symbol. So this was good enough integrity measure back then. So by placing a seal on the envelope, we can ensure the integrity of the letter, right? So if this was broken, then we know that something bad probably happened to the letter. So this is how people back then knew how if the integrity of the letter was broken. So you shouldn't confuse confidentiality and integrity here. So confidentiality, there's no confidentiality guarantee, right? If this seal is broken, after you detach this seal and open the letter itself is not encrypted, right? So there's no confidentiality guarantee there. It's just about integrity of the message. So nowadays, we still use one of these, but it's not for integrity anymore, right? It's just to make the envelope pretty. It's an ornament. Nowadays, we use digital seals or digital hashes to measure the integrity of the data. So whenever you download something from a website, in this case, it's the Ubuntu installation disk file, the ISO file. You've probably seen one of these, right? They show you there's this hash value, and you can compare compare the hash of the downloaded version to the original known good hash value. You can ensure that every bit of the ISO file that is now downloaded onto your computer is exactly the same as the original version, right? If one bit is corrupted in the downloaded file, even one bit, it'll yield completely different hash sequence. So this is how we know that the integrity of the file that you downloaded from the internet has been preserved. So we use hashing algorithms, which we're going to get to create signatures like this that carries the integrity of the data. What are some other examples of hash functions? Anyone? So there's SHA and then MD5, right? MD5 is probably the most well-known one. So mathematically speaking, what characteristics do these functions have? What's one thing that's really cool about these functions? Non-reversible, exactly. AKA one-way functions, right? So hash functions are interesting because they are mathematically they are one-way functions. You cannot reverse the computation, meaning you can go from this 1 gigabyte file to this sequence, but you cannot go backwards, obviously. So the only way to check this integrity is to reproduce the hash signature using this file and the same algorithm and see if they match. Right? So that's why they give you this hash sequence so that you can compare. Do your own computation and compare. So this is how hash functions work, and it's not these files that we use hash functions, but as you're gonna see, this is used everywhere in our and in any secure communications. So yeah, confidentiality and integrity of your connection, for example, to iCampus is being assured by HTTPS. So you know this HTTP, and then there's S, and you probably see this lock icon in front, right? So this means that your connection is secured by a protocol called HTTPS, which is simply HTTP plus TLS. TLS stands for Transport Layer Security. So who here has taken some kind of network course? TCP, UDP, HTTP, right? So in modern communications, we build kind of a secure channel, encrypted channel on top of HTTP or TCP, where the confidentiality and integrity of your connection is guaranteed. At least by today's standards, but so it is secure. So confidentiality is guaranteed by using a shared symmetric key between you and iCampus. So you and iCampus have same set of keys. You encrypt using the key, and with the same key, iCampus decrypts. So therefore, the message is only known to you and the iCampus server. So this prevents eavesdroppers. So if I use, so you probably use Wireshark in your network course, right? So if I run Wireshark in this room and capture your packets, I can capture your packets, but I cannot read the contents of the packet because the key is only known to you and iCampus. Which also means that key is per connection, right? I connect to iCampus, you connect to iCampus, but the key I use with iCampus and between you and iCampus are different. Right? So even though I capture your packet, I cannot read it. So that's the very definition of confidentiality. Right? But what I can do is I can corrupt your message, right? So I capture your packet, I can modify maybe a few bits and then relay back to iCampus. Right? That is still possible. It's just that I don't understand the message, but I can still corrupt it. And that's where integrity or hashing functions come in. So HTTPS or the TLS cipher suite is a combination of multiple cipher suites, meaning it encrypts, it also generates hashes. As we're gonna learn later, it does what we call the key exchange. So modern secure communications have something like SHA or MD5. MD5 is not used anymore much because SHA is considered safer. So it uses SHA to create hashes for each message. So at the end of the message, the hash value is attached. So iCampus gets your message, and if the hash doesn't match the original message, then it'll know something went bad, right? The message was corrupted. So yeah, when you see this icon, it means that both confidentiality and integrity are guaranteed. So I think it started like 2 years ago or last year. The major browsers like Chrome or Safari, they started banning non-HTTPS websites. So if you try to connect a website that is without the S support, I think you see the red message screen says you have to either click advanced and proceed. So by default, modern web browsers refuse connecting to plain HTTP websites. or you get some kind of warning here. So instead of the lock icon, I think you get that the triangular warning sign here. So that's what it means. That means your message to that website is not encrypted, or it can be modified. And the last edge of the triad is the availability. So availability is defined as the following. So for any information system to serve its purpose, the information must be available when it is needed. Am I speaking too fast or too slow? Good? All right, so I think having an attack example just would very clearly explain this this objective of information security. So what attack destroys availability? So you've seen this attack all over the news. DDoS, right? DDoS is an attack that destroys availability. So DDoS stands for, in case you haven't heard, it stands for Distributed Denial of Service. So it's basically millions of computer systems trying to connect to a target website in a very abusive way. So it'll do everything to cause load on the server and cause delays. So the server goes down eventually. So it's kind of like you guys try to call my office all at the same time, right? And this type of attack is very difficult to prevent and at the same time very effective. And DDoS is obviously a direct attack to the availability of any computing systems. So does anyone know how attackers actually prepare for DDoS? Yeah.
They infect like other users, like a bunch of computers.
Right, exactly.
To, like, use their malware against it, like zombie. Is there anything?
Right. So yeah, exactly. So yeah, so the state of DDoS attacks today. So people distribute malware either through something like torrent or in worst case, there are zero-day vulnerabilities. Zero-day, anyone? Zero-day. So you have heard of what zero-day vulnerability is, right? So zero-day vulnerability means there's a vulnerability that has not been acknowledged by the government officials or Microsoft, Apple. So vulnerability is unpatched. So it's still in your system. And attackers write attack code, just like the ones that you're going to write in this course, in JavaScript. So you connect to the website, you download the JavaScript .js file, and then you execute it inside your web browser. And it'll hack your computer and automatically install malware. So that's one source of malware infection, and your computer becomes a zombie computer. And other cases are, spam mail. You clicked on the link, or you downloaded torrent. So there can be many ways your computer can get malware, and they use your computer to perform DDoS attacks. So they don't buy millions of computers. They use yours. So I've been doing the dark web research a little these days. And what we discovered was that the infected computers, access to infected computers are sold like a commodity product in dark web. So someone infects, for example, 2,000 computers, and they're going to sell the access to those zombie computers. So you can actually buy without doing the operation yourself. So there's like a chain of economy going on. People want to DDoS, buy zombie computers. People make malware, so it's like a whole chain So it's an economy. Anyways, DDoS is a direct attack to availability. So you probably heard of authentication and authorization before. So can anyone explain the difference? So what is the difference between authentication and authorization? Yep.
Authentication means that just who you are.
Right.
And authorization is, so can you do this?
That is the exact answer. So authentication means the process of verifying your identity. And one example is the Touch ID. So obviously this slide is kind of old. It's Face ID now, right? So authentication is about verifying your identity, checking you are really who you are, who you saying you are, right? So that's the definition of authentication. And commonly we use ID and password pair, Face ID on your iPhone. We use that pattern thing on Android smartphones. And passports. Passports are government issued your ID. On the other hand, authorization is a security mechanism that determines your privilege or access levels with respect to the system resource, such as computer programs, files, services, and so forth. So authorization often means, so no one really has this in their dictionary. So by saying authorization, people usually mean both authentication and access control, right? You're not authorized to do this. Means either you're not authenticated or you're not authorized. So we can take the iCampus website as an example. Authentication means you log in with your SKKU ID and password. So authorization, so access control is what achieves authorization, right? Access control is a method that achieves authorization. So there's access control on iCampus, if you haven't noticed. So for example, I can make changes to all your grades and everything, whereas our TA can also change the grade. But for example, the TA cannot cancel the course. So there are 3 levels of privileges, right? The instructor, TA, and the students. And this is often called the role-based access control, as you're gonna learn. And we can see how authentication and access control are implemented in the iCampus website. So access control is a security technique that regulates who or what can view or use resources in a computing environment. So access control is what achieves authorization. So if you have used any Unix or Linux-based system, you've probably seen one of these, right? So if you have experience with Linux, you've probably seen something like this. So so who doesn't understand this permission strip from Linux systems? I guess everyone has seen it sometime before, right? So RWX stands for read, write, execute. And the first 3, what D here just means is directory, right? So first 3 means, first 3 are for the user, which is me. And the next 3 is for the group. So this is owned by me, and this is owned by a group called staff. And the last 3 are for the others. Can someone other than me or the staff access this file. So this permission strip says that only the owner can read, write, or access, while the group and the others cannot do anything. Access denied, right? And probably something like access control like this is implemented in the iCampus website. So they probably see that I'm the instructor of the course, and therefore I can make changes to the resources, while the TA, I guess TA belongs to the staff. So if you're in the group, then you can do certain things, but not some things, while the others, I guess the students, can only do can only submit their homework, basically. So this is access control. And another term that might appear quite often in information security is the attestation. So attestation means the action of being a witness to or formally certifying something. So in any app store that we use, Apple, Microsoft, these companies are witness of the app's integrity and identity, right? So every time you download an app from App Store, the apps that are sold or provided in the App Store are signed by the developers. So the hash value of the app and also the signature of the developers are verified by the Apple, and Apple also signs the app digitally, right? So this way, we say Apple or Microsoft attests the integrity of the app, which is signed by the developer and also the owner of the App Store. And in case of HTTPS, certificate authorities or the CAs play the role of a witness and ensures the identity of the website. So you've probably seen something like this. I think Windows also have this. So if you download a executable file, .exe file from the internet, you try to execute it, there's always some kind of warning, right? This is downloaded from the internet, you shouldn't execute this. You probably get this message. Well, the question is, how does the Windows or Mac OS know that the app is not from their certified developer? It's because of these signatures, right? So this is how app stores keep their ecosystem safe, by attaching the integrity and also the signature of the trusted developers in their apps. So they're doing some kind of attestation service in that sense. So in HTTPS, same thing happens. So web servers are required to provide the client or your web browser a certificate. And your browser queries the certificate authorities to check the validity of the certificate. So who remember those, you know, in Korean banking system, we used to carry that USB stick with our keys inside, right? You have to plug that in to be able to do any kind of banking, right? Or maybe you guys are too young to have experienced that. Anyways, so the system is called public key system. So we're going to learn that when we learn about crypto. But it is some type of certificate system that government guarantees that the the certificate you carry is valid. So the question is, okay, so I already explained how you and iCampus communicate over a secure channel. So you're talking to iCampus server, right? So iCampus gives you a certificate, and it says, I'm iCampus, I'm authorized by the SKKU, and let's do a secure communication. You start sending your homework and other information. But how do you really know the server you're talking to is iCampus? Right? So that's why we need certificate, but certificate has to be, the validity of the certificate has to be guaranteed by someone. And that someone is called certificate authorities. If you're confused, that's fine. So we're going to learn about this more in crypto, so let's move on. All right, next we're going to discuss security design principles. So this is from a very, very old article from Sulzer and Schroeder's 1975 article, The Protection of Information in Computer Systems. So it has 9 principles: least privilege, fail-safe defaults, economy of mechanism, complete mediation, open design, separation privilege, least common mechanism, psychological acceptability, defense in depth. So it's really interesting that this article is almost 50 years old now, right? And this was written in the very beginning of the, basically around the birth of computing systems in the 70s. But most of these principles still hold and also still widely used in secure design of computing systems. So the least privilege principle. A user or a component must be granted a minimal set of privileges that satisfy its requirements. So in short, this says that a component must be given just enough privileges for it to function. And the next is fail-safe defaults principle. Okay, so before we move on, so what's an example of least privilege principle implemented in computing systems? Especially in access control, this is a very common principle used in access control systems. Yep.
Making sure that only like the administrators have rights to like read and execute. I mean, to have rights to execute files.
Can you think of an example in your smartphone apps, perhaps?
Smartphone apps. You have to be signed in to your iCloud to be able to access your apps.
Close. What about like third-party apps? Like camera filters and.
You have to allow access to be able to activate the camera in the app.
Right. So operating systems gives initially no privilege at all. Then if you try to take the picture, then it'll ask you, do you want to allow access to camera for this app, right? So we don't want some kind of image filter app to have access to mic and everything. So we disable everything by default. And we only want to allow the least privilege to the app, which doesn't work really well, right? Because we just click OK anyway. We don't care. Okay, the next is fail-safe defaults principle. So this one is about. Unless a subject is given an explicit access to an object, it should be denied access to that object. So going back to our image filter example, the default must be no privilege allowed, right? So that example I just explained is a combination of number 1 and number 2, least privilege and fail-safe default. And access decisions must be made on permissions rather than exclusion. So basically this says default action should be access denied. So let's do a case study. So this was the example that I was talking about, right? So everything should be denied by default, and it'll ask you if you want to allow access to a certain resource. So it is kind of split up into multiple categories to allow least privilege, right? You don't want to allow camera access and mic access at the same time. So those are two different resources on the system. So you have to, so these are split so that it can be applied in a least privileged manner. But we ignore this anyway, right? By just looking at this, you want to click OK immediately.
But I think there is a new option that says allow this time or allow only.
Oh yeah, that's a good point, right? So this is kind of old, but nowadays, yeah, the location tracking, right? Do you want to allow all the time or once? So that's another more least privilege than the previous version. Okay, so this is so CVE stands for common vulnerabilities and exposures. So this is the database where we keep vulnerabilities found in information systems, any kind of system we use today. So it's got billions and billions of vulnerabilities. So this is where all the vendors and manufacturers report the vulnerabilities they found, and they register that to this database. So all vulnerabilities that we know are registered in this database. So when we discuss certain vulnerability, especially security researchers, we don't say, oh, do you remember that vulnerability in macOS that we found 2 weeks ago? We don't do that. So we use this code name. Did you look at how CVE 2023 1112 was done, right? So every vulnerability has a code name, unique identifier, and this is what this is the very purpose of the database. So you can look up any vulnerabilities that we found so far, and you can look at their description, and sometimes they even have the proof of concept code.
Is it easy to filter it so that you can limit your search?
Yeah, you can search it by type of vulnerability, like is it stack buffer overflow, heap overflow, is it on Microsoft Office? So you can search by type and also the product name.
And how do you upload to this? In terms of if Microsoft found a vulnerability, do they have access to upload or something, or does it go through review?
Yeah. So you can turn in your report, and they're gonna review, and then when they if they confirm that it is actually a vulnerability, they give you a code name like this, and also they determine the severity level. Is this a complete catastrophe, or is it just a minor bug? Oh yeah, so the point that I was trying to make here, about fail-safe defaults principle. One common case, so one of the most common case or type of vulnerability in the CVE database is the unsafe default values. Do you know how when you buy a new wireless router or printer, there's always some kind of default password, right? It's either admin or admin, so that's the default value. But it's not fail-safe, right? Everyone can guess. So if you see a new wireless router on the network, you can just try admin, right? Actually, there are attacker groups that actually actively try to find any IoT or printer devices on the internet, and they will just brute force. They'll try admin, or some other default passwords. So this was one of the most common vulnerabilities in the CVE database. And this is a really good example of fail-safe defaults, principles gone wrong, right? But I think things have improved nowadays, right? So I think I actually bought a wireless router sometime last year. And instead of just doing admin, nowadays the products have some kind of randomized default password on the bottom. So things have improved. So that's a fail-safe default, having a randomized default password on the product, whereas admin is not fail-safe. So you can look up these vulnerabilities. So this is usually what it looks like in the description tab. So in this case, SSL, TLS is not used, so people could eavesdrop on this communication. So antivirus software installs important files, important configuration files to a folder that basically has open to everyone permission. So basically any software installed on the system can modify the settings on the antivirus. So this IoT device has default Wi-Fi credentials that are exactly the same for every device. So if you sell 3,000 IoT devices, 3,000 systems have the same password. And of course, a fail-safe option would be randomized default passwords for each one of these devices. The third one is also very interesting. It is called economy of mechanism. So this one is basically about that security mechanisms should be as simple as possible. Complex mechanisms may not correctly work because it is difficult to understand, difficult to model, difficult to configure and implement. So software must be sufficiently small so that it can be verified and implemented. Okay, so let me think about an example of this. So let's say our iCampus is very, very critical, and hackers want to steal information from iCampus. I guess one way to secure the website would be to force everyone to do two-factor authentication every time you do something, right? And on top of that, I think we can also deploy some kind of CAPTCHA system. So every time you try to access iCampus, you have to do two-factor authentication and CAPTCHA. That makes the website very, very secure, right? But where it fails is the economy of mechanism. So it's too much work for the users, and we can see that that's probably not going to work out. So this principle basically says that the security mechanism have to be convenient and economic. And number 4 is complete mediation. Complete mediation means that every access to every object must be checked. Access to all objects must be checked against the permission every time. So default mechanism for today's access control system, of course. So every time you access something, any link on iCampus, it has to be checked, right? So you guys are all 3rd grade or 4th grade and probably learned about the kernel, the OS kernel in the operating systems course. And you probably remember the system call interface, right? System call. And you probably learned that any sensitive operation that directly done to the hardware are all under kernel's control. So can you really access a file directly in the user space? So you're writing a program in C, can you really access a disk? And then how does it usually work? So you yeah.
The user puts in, what are they called? They're like push it, like it's like on signals, like something signals that like to indicate like off, leave, execute, stuff like that. System calls.
Right, exactly, yeah. So yeah, so you probably do something like include stdio, stdlib, so that is called the C library, right? And you use C library functions, fopen, read, but internally all those functions eventually have to call the system call, like sysopen, sysread. So that's how user and kernel communicate with each other. So every access to the hardware have to come through the kernel, and only the kernel can access the hardware directly. So this is an example of complete mediation. So you cut off access to hardware completely. So user cannot do anything with the hardware directly, and everything has to go through the kernel. Therefore, you can check every operation of the user programs in the kernel space. So this is an example of complete mediation. So whatever you do, you cannot directly access the hardware. You always have to go through the kernel. So yeah, even though you feel like you are talking to the hardware directly, but everything you do have to go through the kernel. But we don't feel that because we all use the libraries or runtime, right? So even though you use something like JavaScript, Python, you feel like you're communicating with the hardware, but underneath, everything you do have to go through the kernel, and kernel checks the permission of your operation through the data structures that it maintains. Okay, number 5 is called the open design principle. So security of a mechanism should not depend on the secrecy of its design or implementation. In other words, complexity does not add security. So it advises against what we commonly call security by obscurity. So what's an example of security by obscurity? Yep. Okay, let me show you a good example here. So this is security by obscurity, right? So the security of the security mechanism depends directly on the secrecy of the mechanism itself. So if someone finds out that you're hiding key under the rock, then they're gonna find the key every time, right? So in this case, the security of the key solely depends on a single information. So this is not what we call open design principle. So we already discussed the hashing functions, right? We have SHA-256, MD5, and we're gonna learn about different types of crypto systems in this course, including the public key systems such as RSA or symmetric key crypto systems such as AES. Surprisingly, none of these are closed source. These are all open. Everyone knows how they work. Everyone can see the implementations of these. So these are all open. So everything is open when it comes to security. So anyone can study. It's not just the crypto systems, but all the security mechanisms in general are open. And if it's not open, I don't think people will trust such a mechanism. So anyone can study its inner workings, and it is still reasonably secure for most of us, the AES and RSA. So because they're open, there have been vulnerabilities found on these crypto systems before. So anyone can study their algorithm or their implementations and find problems and report them. So open design principle is the default in today's secure systems. So number 6, separation of privilege principle. A system should not grant permission based on a single condition. It requires multiple conditions to grant privilege so that we can remove a single point of failure, and we can separate the components by importance of their role, duty, or hierarchy. And this is often combined with least privilege principle. So if we're going to separate the privilege, we have to make it also least privilege. So our political system also practice this type of safety measures, right? Separation of power and also least privilege. So we don't want the executive branch making legislative decisions all at the same time, right? So we want them to be separate, and at the same time, we want them to be least privilege. So this is our political systems today, and a really good case of well-implemented least privilege and separation of privilege is actually Chrome browser that you're probably using right now, right? You probably have the Chrome browser open. Okay, so let's skim through. So this is from the Google's architecture, Chrome browser architecture document. So as users spend more time in the browser and do sensitive stuff, it is increasingly important that we provide the most secure environment that we can, right? So we operate with the principle of least privilege. So we security researchers know where this term is from. It's from that 1975 really old document. So we operate with principle of least privilege to the extent possible. So every code is sandboxed, and its privileges to interact with the host system are restricted as tightly as possible. So untrusted is never handled in privileged code, instead passed off to a sandbox code for consumption. Okay, so first of all, we know that Google is trying to pursue least privilege here. And at the same time, the code is sandboxed, and every interaction with the host system are restricted. And this is about complete mediation, right? You put it in a sandbox and you try to control all the interaction with the host system. Kind of like how you have to make system calls if you want to do anything. So least privilege, separation of privilege, complete mediation. Everything's kind of built into the design of Chrome browser. It's actually really interesting. There's an academic paper on the design of the Chrome browser. And I think it's very old, so I don't know what improvements have been made to the browser. But Chrome browser is basically like a whole setup system. So it has a browser kernel, which has the full privilege, kind of like how we have the real operating system kernel. So only the kernel has the full privilege, and the rendering engine and other components contain each privilege within itself. So everything is sandboxed, everything is separated. So according to the paper, all these components are split into different sandboxes, and each sandbox only does one thing. So HTML parser should only access HTML objects, and CSS parser should only do its job, and everything else is just completely separated into sandboxes. So this is the general design of the Chrome browser. So as you can see, everything is separated into according to their task, and everything has a very strict data flow. So complete mediation, least privilege, separation of power. But one problem of this design is that since we want to separate everything, everyone has to have his own room. Right? That's the idea behind complete sandboxing and complete mediation. As a result, it consumes a lot of memory. So that's one of the reasons why Chrome is very memory hogging software. But if you are to put everything in a single process, single memory space, then we would probably use less memory, but we're not going to achieve separation of privilege. So separation of privilege is also in operating systems, right? Going back to the system call example, only the kernel can interact with the hardware, whereas user cannot. And this is actually built into the modern CPUs. So CPUs distinguish different execution modes. So when you're executing in the kernel and user, you are actually executing in different mode of operation. So for x86, when you're in the kernel space, you are executing with the ring 0 mode. When you are executing in the user, you are executing with the ring 3 privilege. The difference is that you cannot execute privilege instructions. So if you recall the x86 instructions from system program, so besides the instructions that you learned, there are privilege instructions that only the kernel can use. So since you cannot use this in the kernel, in the user space, you can only do certain things in the user space. So if you try to execute these instructions in the user program, the program crashes. And of course, you cannot access supervisor pages. So who remember the virtual address mapping in the kernel and the user? No one? Okay, so in the same virtual address space, there's a user program and also there's a kernel, right? Kernel's in the memory. But you cannot access kernel memory because the CPU distinguishes user pages and supervisor pages. And if you try to access supervisor page from user, the program crashes. So the separation is based on the processor privilege levels. So we can see that computing systems, starting from the CPU, we have separation of power. So some of you might be wondering, so we have ring 0 and ring 3, right? For kernel and the user. But why aren't we using the ring 1 and ring 2? So I had the same question. So if you're interested, you can read my paper. So basically, in this paper, I proposed that we can have a middle ground between the user and the kernel so that we can store more important user space components such as cryptographic keys and so forth. So if you're interested, you can, yeah.
And are the ring 1 and ring 2 different in any way, or they're the same?
In terms of privilege, they're the same.
Okay.
Yeah. Do you have some x86 architecture background?
Kind of.
What from what? From reverse engineering or?
Yeah, reverse engineering.
Okay. But typical user program reversing don't give you, these type of knowledge. What kind of project did you?
So I'm trying to remember, and I think it wasn't in reverse engineering. I think I took another course that talked about this. And it was,
OS?
or it was computer networks or something like that. I'm not sure.
Okay. Yeah. Anyways.
I can read the paper.
Yeah. All right, I'll highly recommend it.
Where could we find it?
You can Google the title of the paper. So it's called Lord of the x86 Rings. Anyways, so number 7 is least common mechanism principle. So mechanisms used to access resource should not be shared, or sharing must be minimized. So given two different services with different priority, the more resources they share, the more likely one can influence the other. So this is actually a huge issue in today's information security academia. So sharing is not caring. It's actually a source of side channels. All right, so this is now like a cliche tech company interview question. I think many of you has already heard this. So who knows this problem? The 3 switches and 3 light bulb problem. Okay, don't spoil it for everyone else. All right. So you enter a room and you're given 3 switches in room 1, and you are permitted to operate the 3 switches. And each switch is mapped to each light bulb in room 2. So you walked into room number 1 and you see these switches, and you're about to enter room number 2, where the light bulbs are actually located in. So you'll be allowed to leave room 1 and enter room 2 to look at those 3 light bulbs, but you cannot go back and operate the switches. So you're in room 1, you operate the switches, and now you move on to room 2. Your job would be to figure out which switches are mapped to which light bulbs.
And you can't see the light bulbs once you enter the rooms?
so when you're in the switch room, you cannot see the light bulbs. But to see the light bulbs, you have to move to the other room where you can no longer operate the switches.
So if you go to room 1, click it, and then you'll see which one's like on, then you go to the next room, switch it, you see the next one.
Oh, you cannot see the light bulbs in room 1. So room 1, you only have the switches.
And all of them are off?
Hmm?
All of them are off?
Yeah.
Okay. So, you have to switch it to room 1.
Professor,
Yeah.
is it traditional light bulb or modern light bulb?
What difference does it make?
Traditional light bulb can be very hot when
Yeah.
But
I would say traditional. Yeah.
Once I come out of room 1, I can see the light bulbs now.
Right.
And I'm only allowed to flick it once, right?
No. You can operate it as much as you want. It's just that if you leave the switch room, you can no longer touch the switches.
I might be like misinterpreting it, but it just seems like if all of them are off, you go into room 1, you switch the light room 1 on, and then you go up, and then you can see which one is on now.
Right.
It's mapped to room
Exactly.
1. You go to room 2, you do the same thing. Now you know it's mapped to room 2. Room 3, you do the same thing.
Yeah. So assume there's a wall here, right? So this is room 1.
Uh-huh.
So I have my 3 switches. So I cannot see the light bulbs,
Yeah.
but I'm allowed to operate it. So I do whatever I like to do with the switches.
Mhm.
Then I open the door, and
Oh,
move,
you can-
move to the room 2, and then I have to close the door.
Uh-huh.
At this point, I cannot operate the switches anymore.
Uh-huh.
But I can see the light bulb and which ones are turned off.
Yeah. The room
Yeah.
that you just like, you turn that one on.
Yeah.
You go outside, you see that a light
Yeah.
bulb just turn on. That one's mapped. I don't know. I might be.
Then how do you match like which one's which the switch to light bulb? How do you?
You only see the light bulb that was on at the end, or is it like as soon as you exit room 1?
As soon as you leave the room 1.
I switch room 1. When I'm in room 1, I click it on. I go to the next room. I see
Right.
that one light bulb's on, and then the second one I switch that one on, and then when I'm in the third room, I see the second.
There's no room 3. There are only 2 rooms. 3 switches in room 1. 3 light bulbs in room 2. They're connected to each other.
Okay, I see where I go wrong.
There was a really critical hint.
Yeah.
We just heard.
because light only has a 0 and 1 state,
Mm-hmm.
and if there is discrete in 2 states,
Mm-hmm.
I think the temperature must be the one which can compare to.
Right. That's the correct answer.
Okay.
So you turn on 1. So you operate 1 switch. You turn it on. Then you maybe wait for like 1 minute. Turn it off. You turn on the second one. Then you go into room 2. So there should be one that is currently on, right? So this must be from the second switch that I just turned off, right? So between the 2 turned off light bulbs, one must be hotter than the other.
Okay.
So that must be the first one, right? That I just turned on and off, right? So this was, from what I heard, interview question at Microsoft. I mean, imagine walking into the interview room and being asked this question. Anyways, nowadays it's a cliche. I think it's a well-known, like a tech company interview question. Anyways, so this shows, this illustrates how modern cache side channel attacks are done. So this is the answer. Turn on 1, wait 5 minutes, turn it off, turn switch 2, and then you go into the room. So off, on, hot. Okay. So the problem is that similar phenomenon happens within our CPU. So in many processor architectures, I think if you have taken computer architecture, you probably learned about the caches and the level 1 cache and also the last level cache, which is, in case of x86 is the L3. So these are all shared among the cores, right? So multiple processes share L3, But the bigger problem is for instance, the cloud. So everyone's sharing this processor. So these multiple processes they have different owners. And we're going to discuss the rest next time.